Hey everyone, welcome to our vlog. We're a group of aviation-obsessed students, and today we're diving into one of the biggest breakthroughs in modern flight, space-based air navigation, or more specifically, GNSS, the Global Navigation Satellite System. Now, you might have heard pilots or air traffic controllers talk about GPS, RNAV, or RMP, but all of that is rooted in GNSS. It's a satellite-based technology that's replacing traditional ground-based systems like VORs, NDBs, and DMEs. So, we started with one big question. Does space-based navigation significantly improve accuracy, efficiency, coverage, scalability, and safety in aviation compared to the old ground-based systems? Spoiler alert, it absolutely does. But we didn't want to just say that, we wanted to prove it through structured research. Each team member took on one aspect of this hypothesis. I focused on the research method itself, and later on, the safety benefits. The rest of the team tackled accuracy, efficiency, coverage, and scalability. Our process started by breaking down what we already knew, or thought we knew, about aviation navigation. Then, we dove into technical manuals, ICAO documents, academic journals, and real-world case studies, like how GNSS has changed operations at airports in Alaska, or what happens when GNSS fails over Europe. We also looked at pilot forums and interviews to understand how crews actually feel about GNSS in the cockpit. Each of us will walk you through what we found, so let's get into it, and we'll start with the foundation, accuracy.
So, accuracy is the cornerstone of everything that GNSS does. Traditional ground-based systems or NavAids, like VORs, which are short for Very High Frequency, or VHF, Omnidirectional Range, and NDBs, which are non-directional beacons, send out radio signals that pilots tune into and use to navigate. These systems naturally come with very big limitations. First, they degrade with distance. The further you are from a VOR, the less accurate the radio you're flying becomes. And the same applies to NDBs, which are even more prone to interference, especially from weather or terrain. GNSS, in contrast, uses a constellation of 24 plus satellites orbiting around the Earth, and an aircraft receives signals from at least 4 satellites at any one point in time and calculates its position through triangulation, measuring the time delay of each signal to compute an exact 3D location by latitude, longitude, and altitude, and the fourth one can be used for time accuracy. The result, horizontal accuracy is usually within 5 to 10 meters, and it can be even tighter with different augmentation systems, ones that are like WAAS in the United States and EGNOS in Europe. When comparing that to traditional ground-based navaids like VORs, triangulation, which might get you within a few nautical miles, but that's honestly a huge difference, especially when you're flying approaches or flying over mountainous terrains. The nautical mile differences can mean life or death. Now, this level of precision is what makes RNP approaches possible, which are used in airports like Queenstown, New Zealand, where the airport is surrounded by mountains, and yet aircraft can safely fly curved, pinpoint accurate paths down to the runway, all thanks to GNSS accuracy. Without GNSS, those kinds of operations wouldn't just be harder, they'd honestly just be impossible, flat out impossible. Now, it's not just about flying a straight line anymore, it's about flying exactly where you want to, down to the meter, and that's a massive leap from where we once started.
Now that we've covered how GNSS improves accuracy, I'll talk about efficiency, a major benefit for airlines, passengers, and the environment. With traditional ground-based navigation, aircrafts had to hop between stations. Think of it like driving a car, but only being able to steer by stopping at specific signposts on the highway. You would often take indirect routes to connect those points, wasting time and fuel. GNSS breaks that chain. It enables aerial navigation, RNAV, which lets pilots fly any desired route within the coverage area, even curves or shortcuts, rather than zigzagging between ground stations. Then there's required navigation performance, RNP, which builds on RNAV. By adding strict performance requirements, so air traffic controllers know exactly how precise a plane's navigation is at any time. This means flights can take the most fuel-efficient parts, reducing flight time, burning less fuel, and lowering emissions. For example, A flight from New York to London can save up to 100 nautical miles flying optimized routes instead of traditional ones. That's nearly 20 minutes saved and hundreds of kilograms of fuel as well. Efficiency isn't just about saving money though. It also means less noise over communities near airports, because aircraft can climb or descend continuously without leveling off repeatedly, reducing engine noise. This is called continuous descent approach, CDA, or continuous climb, and it's now common at busy airports like Heathrow, Los Angeles airports. Smaller airports also benefit significantly. GNSS allows them to optimize approaches in challenging terrain, avoiding obstacles like mountains or small structures without lengthy detours. In remote regions where ground-based navigation is best, GNSS enables safer, more direct routes, reducing delays and improving reliability. Airlines also see a long-term cost savings. Fewer delays means better on-time performance, whilst reduced fuel consumption cuts operational expenses. Over time, these efficiencies add up, making air travel more sustainable.
Scalability, a crucial factor as global air traffic continues to increase rapidly. Air travel has begun growing steadily for decades, with more people flying than ever before. This puts enormous pressure on air traffic management systems to keep flights safe and on schedule. Traditional navigation systems rely on fixed ground stations and rigid route structures, which limit how many planes can safely occupy the same airspace at once. GNSS, however, supports more precise and flexible navigation, allowing planes to fly closer together safely, both side to side and vertically. This means air traffic controllers can manage tighter flight spacing, increasing airspace capacity without compromising safety. For example, in busy terminal areas, GNSS-based procedures enable parallel approach paths closer than traditional methods allowed. This precision supports performance-based navigation, or PBN, which tailors flight routes and procedures to the navigation capability of each aircraft. Airlines flying more advanced planes can use narrower routes or more optimized paths, while older aircraft follow wider, more conservative routes, all coordinated efficiently. Moreover, GNSS allows dynamic rerouting in real time, so if weather or traffic congestion arises, planes can adjust routes efficiently, preventing delays and reducing fuel burn. In the future, as air mobility and drones enter controlled airspaces, GNSS scalability will be essential to safely integrating these new users alongside commercial aviation. In short, GNSS doesn't just handle today's traffic, it's preparing the way for the complex, crowded skies of tomorrow.
Let's discuss coverage, where GNSS truly excels compared to traditional systems. Ground-based navigation systems rely on radio signals that travel in a straight line, so you need a ground station nearby to pick them up. This limits the range of about 200 to 250 nautical miles at cruise altitudes of around 30,000 feet and above, and significantly less range at 90 nautical miles at lower altitudes of around 5,000 feet or in rugged terrain or bad weather. That's why traditional navigation often struggles over oceans, polar regions, remote land areas that are without infrastructure. The numerous GNSS satellites orbit high above the Earth, broadcasting signals that reach 100% of the globe, with multiple GNSS satellites in line of sight at all times. Because of this, GNSS enables transoceanic flights like those between North America and Asia, which would have been a nightmare to navigate safely if there were only ground stations. It also opens up polar routes. Airlines now use shorter paths over Arctics to cut down flight times, saving fuel and avoiding those air traffic corridors. In fact, ICAO has created the Global Air Navigation Plan, highlighting GNSS as the backbone for the world air navigation by 2030. For pilots flying in remote areas like Alaska's vast wilderness or Australia's outback, GNSS provides reliable, constant positioning even where there is no radar coverage or radio navigation aids. This expanded coverage doesn't just improve convenience, it enhances safety by keeping pilots informed of their positions and others' positions at all times, reducing the risk of navigational errors or being lost. Based on Gamma's report, 80% of all aircrafts are small general aviation planes, which typically fly below 10,000 feet. And knowing that ground-based navigation range drastically reduces at lower altitudes, this causes concern for the majority of aircrafts that cannot achieve basic navigation.
Space-based air navigation improves pilot situational awareness by giving pilots live traffic information. This, in conjunction with ATC, allows pilots to have a better picture of what's happening around them. Before the implementation of ADS-B, pilots had to either rely on their eyes, position reports from other aircraft, or ATC to form an idea of what was happening around them. Pilots had to create a mental image of what was happening, which for even the most seasoned pilot can be difficult, especially in high traffic areas and complex airspaces. With the advent of ADS-B out and in, one for transmitting position and altitude information, and one for receiving that same information from other aircraft, it has allowed aircraft and avionics manufacturers or even app developers to display this information within the cockpit. Cessna, for example, has implemented ADS-B in and out within their new Cessna aircraft, such as the Cessna 172 SP, allowing pilots to see a live display of other traffic overlaid on their glass cockpit maps. By displaying live information of other aircraft around them, it allows pilots to more easily spot other traffic and make better operational decisions. For example, if a pilot was anticipating a turn to the left and didn't spot traffic that was approaching them on their left, the Cessna's automated TCAS, traffic collision avoidance system, would alert them of that nearby traffic once they came within a certain radius, providing a verbal call-out of the position of the aircraft using the clock code, 12 o'clock, 3 o'clock, 6 o'clock, or 9 o'clock, or anywhere in between, and the altitude, same level, high or low. This in turn will allow the pilot to spot the traffic and maneuver around it, possibly by passing a close call. In the world of IFR, Instrument Flight Rules Flying, there exists a set of procedures called instrument approaches. These approaches are used to safely and efficiently land on a runway with minimal visibility and sometimes no external references, such as landmarks or the runway itself. GPS overcomes many of these challenges. It works worldwide, providing consistent, highly accurate positioning, allowing accurate tracking to destinations and approaches with extreme precision.
So, after diving deep into GNSS, from accuracy to safety, it's time to reflect. Did our research answer our big question? Our hypothesis that was space-based navigation significantly improves aircraft navigation in accuracy, efficiency, coverage, scalability, and safety compared to older ground-based systems like VORs and NDBs, that this improvement boosts overall airspace capacity and flight safety. So after reviewing the data, technical literature, and real-world examples, we can confidently say yes. GNSS doesn't just meet these claims, it exceeds it in nearly every way. We saw how its pinpoint accuracy lets aircraft navigate precisely, enabling more direct and fuel-saving routes. We also learned that GNSS global reach overcomes the limitations of line-of-sight ground stations, opening remote and oceanic airspace to safer, more efficient travel. We discovered how GNSS supports airspace scalability, letting more planes share the skies safely through tighter route spacing and flexible procedures. But more importantly, GNSS has enabled or enhanced safety by enabling precision approaches and modern surveillance tools like ADS-Bs. But beyond technical findings, the research itself was quite enlightening. It challenged us to sift through complex, jargon-heavy sources, distill core concepts, and communicate them clearly for our audience, just like we're doing now. It wasn't always easy, simplifying without losing accuracy or finding reliable sources and making sure each team member's section fit together logically. We had to coordinate closely to share drafts and give feedback and rehearse to ensure a smooth professional presentation. So this project was as much about teamwork, communication, and critical thinking as it was about GNSS. Overall, we believe our research has helped us, and hopefully you now understand why GNSS is truly transformative for aviation.
Thanks for watching. We hope you now have a clearer picture of how GNSS is transforming the skies.
From enhanced safety to smarter routing and global connectivity, GNSS is the future of flight navigation.
Most importantly, GNSS makes flying safer for everyone, from passengers to pilots to air traffic controllers.
Clear skies and safe travels, everyone.